Assalamu alaikum and welcome to lecture number 15. In this lecture we are going to discuss the system function for the system characterized by linear constant coefficient difference equations. You understand LTI system can also be represented as linear constant coefficient difference equation. You know that discrete time LTI system can also be represented by linear constant coefficient difference equation. The discrete time filters are most typically realized through the implementation of LCCDE. A typical equation is summation k running from 0 up to n a k y of n minus k is equal to summation k running from 0 up to m bk x of n minus k. So applying the z transform to both sides of this equation will result into ak z of minus k y of z. You understand k represents the delay in the yk, right? Y of n. So that means y of minus 1 will have y of n minus 1 will have the z transform y of z into z power minus 1. So generalizing it to k, it will be the z transform of y n minus k will be y of z into z power minus k. So we can also write it z power minus k, and because the z transform is linear, so that means scaling the input will result into scaling the z transform by the same factor. So that's why we can write ak z minus k y of zk. Similar argument applies to the right side of the equation, and we have summation k running from 0 up to m bk z power minus k x of z. Or we can take the y of z common from here and x of z common from here. So you understand the system function is y of z divided by x of z. So we can write it like this. So we can write h of z equals to y of z over x of z, and this is equal to summation k running from 0 up to m bkz power minus k and divided by summation k running from 0 up to n akz power minus k. So I think this type of problems you have already done. So this can also be written in the factor form. So we can write it like b naught over a naught and product k running from 1 up to m 1 minus ckz inverse over product k running from 1 up to n 1 minus dkz power minus 1. Now each factor in the numerator, that is 1 minus ckz inverse, contributes a 0 when z equals to ck. So you understand when z equals to ck, so z, and because this z inverse, so z multiplied by z inverse will result into 1, and 1 minus 1 will result into 0. So h of z becomes 0. Similarly, it also has a pole when z equals to 0. So replacing z equals to 0 here, so this z power minus 1, so it can be written as 1 over z. So when z equals to 0, 1 over 0 will result into infinity, and h of z becomes infinite when z equals to 0. So that's why we say the each factor 1 minus ckz inverse contributes 0 when z equals to ck and pole when z equals to 0. Similarly, for the denominator terms, each factor, that is 1 minus dkz inverse, contributes a pole when z equals to dk. So you understand when z equals to dk, that means dk will be replaced by z. So z into z inverse will result into 1. So that means 1 minus 1 will become 0. So this divided by 0, 1 over 0 is basically infinity. So that's why it will contribute. This is how, in fact, it will contribute a pole. Similarly, when we replace z by 0, so because this is z inverse, that means it's 1 over z. So when z equals to 0, 1 over 0 will be infinity, and 1 over infinity will be 0. So that's how it contributes a 0 and a pole. So let's have a numerical problem. Here we need to find the difference equation for the given system function. So h of z equals to this one. So you know h of z basically equals to y of z or x of z. So we can multiply by cross multiplication. We have this term, right? This multiply with y of z, and this is equal to x of z. Now taking the inverse z transform, you know y of this will have the inverse z transform as y of z plus 1 over 4 y of z z inverse minus 3 by 8 z power minus 2 y of z. Okay, so the inverse of y of z will be y of n, and this is 1 unit delayed, so it will be y of n minus 1. So the scaling is same, so 1 by 4 y of n minus 1. Similarly, minus 3 by 8 y of n minus 2. Again, for the right side, x of z multiplied by 1 will result into x of z. So inverse z transform of x of z will be x of n. Again, this is 2 scaled by a factor of 2, and this is 2 times x of z z power minus 1. So that means this is scaled by a factor of 2 and shift by a factor of 1. So this is 2 times x of n minus 1, and similarly the second term that's delayed by a factor of 2 units, so it's x of n minus 2. So this is the required difference equation. Then we come again with the two terms, stability and causality, and you know both the terms very well. So in time domain, for a system to be stable, its impulse response must be absolutely summable, right? And because you also understand that the z transform is valid for both stable and unstable systems. So in case of z transform, we have mathematical expression and the ROC. Now for a ROC, for a system to be stable, ROC must include the unit circle. If this condition is satisfied, then we say the system is stable. If ROC does not include the unit circle, then although the z transform for that system response exists, but that system is not stable. Similarly, causality implies that ROC must be outward from the outermost pole. So for a system to be causal, the impulse response must be right-sided. Okay, that's very clear to you because these things we have done so many times. Now the next thing is for a system to be both stable and causal. So you understand, for stability it is must that ROC includes the unit circle, and for causality it is must that the ROC must be outside the outermost pole. So all poles of the system must lie within the unit circle. So for, let's have a numerical problem on finding the system function, and we need to plot the pole zeros, and we also find the ROC for the system described by this difference equation. Okay, so I leave it as a homework for you, and in the class we'll discuss what do you get and how do you satisfy that when the system what should be the ROC in case the system is stable, in case the system is causal, or in case both the system is stable and the causal. So the next topic is the inverse systems. So you understand first to describe the inverse system, let's first define the invertible system. So you understand a system is said to be invertible if distinct input produces distinct output. And you understand, for example, there's a system that takes the square of the input, so in this case the inverse system will not exist because a distinct input does not lead to distinct output. For example, for the case of squaring system, if the input is 5, then the output will be square of the input, which is 25. And similarly, if the input is -5, again we get the same output, which is 25. So that means although at the input we have two distinct numbers, two distinct values, but the output does not contain the distinct values. So that means the inverse for the squaring system does not exist. So if the distinct input leads to the distinct output, in that case the system is said to be invertible, and for the invertible system the inverse exists. And we have done this while doing the topic on signal and system, and you know that if the system is invertible, if it is cascaded with the inverse system, then the output will be equal to whatever you give it input. So for example, in time domain we say we have a system which is represented by h, whose impulse response is h of n, and we have another system which is cascaded in series with it, and which is inverse of it, denoted by hin. So if we convolve the two systems, the result will be impulse. So you understand, in case of the Fourier, or in case of the Z domain, in Z domain convolution becomes the multiplication. So let we represent this system in Z domain by G of Z. So H of Z is the Z transform of H of n, and similarly Hi of Z is the Z transform of Hi of n. And because in time domain they are multiplied, so in frequency domain they will be in time domain they are convolved, so in the Z domain they will be multiplied. So the product of 2 will result into 1, because the Z transform of impulse of n, it will be 1. So what is the relationship between the system and its inverse? So that's quite straightforward. Hi of Z will be equal to 1 over H of Z. So that's the relationship for the inverse system. Similarly, for the system taking in the frequency domain, so in frequency domain we can say the relationship between the system and its inverse system, provided that the inverse system exists, will be Hij omega will be equal to 1 over Hij omega. The log magnitude, you understand, magnitude expressed in logarithmic scale. Phase and group delay of the inverse systems are negative values of the corresponding functions for the original system, right? So whatever the original system has these values, they will be negative in the inverse system. Again, you understand that not all systems have the inverse, right? So for example, ideal low pass filter does not have inverse, because when you low pass a signal, the higher frequencies are removed, and you in no way you can reconstruct them. So it doesn't have the inverse system. The class of system with rational system functions is an example of system which do have inverse. So in that case, the poles of the inverse system are the zeros of the original system, and similarly the zeros of the inverse system are the poles of the original system. And because we also need the region of convergence in case of the Z transform, so if we are in Z domain, that means the rock of H of Z and Hi must overlap. Now if the H of Z is causal, its rock will be absolute of Z greater than the maximum pole. Okay, so any appropriate ROC for H inverse of Z that overlaps this region is valid if rock for right. So let's consider we have the system function H of Z as defined here. So its inverse will be the reciprocal of it, right? So that means the zeros here will become poles for this system, and poles of this system will become zeros of this system. So B naught upon A naught will become A naught upon B naught, and similarly this will come here, and this will come here. Okay, let's consider a numerical example. For example, we are given a system which has the response equal to 1 minus 0.5 Z inverse over 1 minus 0.9 Z inverse. Let's find the inverse of this system and also find the impulse response of the inverse system. So you understand, for the inverse, the poles of this will become zeros of the inverse, and zeros of this will become poles of the inverse. So that means we can write H inverse of Z, and this is equal to poles here are these, so we can write 1 minus 0.9. now this will be zeros, and the zeros of the original system will become poles of the inverse system, so that is 1 minus 0.5 Z inverse. Okay, now the ROC for this is ROC for the original system is that absolute should be greater than 0.9. Now for the inverse system we have the choice, and because we know that the inverse system, the relationship between the ROC of the inverse and the original system is, now for the ROC of the inverse system we have choice that either absolute of Z should be greater than 0.5 or absolute of Z should be less than 0.5. But according to the given condition, that the ROC of the original system and the ROC of the inverse system, they must overlap. So in this case we are left with the choice that the ROC for this system will be absolute of Z should be greater than 0.5, because only then the two ROCs will overlap, that is ROC of this one and ROC of this one. So now knowing the ROC, now we can find the impulse response of the inverse system. So that's quite straightforward. I think you can do it quickly. There are different ways you have been taught, and you know how to use them. So for me the easiest way will be the inspection method, and what we can do, we can express it as this one. Okay, so we can express it as that's your H inverse of Z, and we can write it like is equal to 1 over 1 minus 0.5 Z inverse, right, and minus 0.9 Z inverse over 1 minus 0.5 Z inverse. Okay, so now we have split it into two, so you understand, because if you compare with the generalized form is that A of n, that's for the right sided sequence, right? And because the ROC tells that this sequence is also right sided. Okay, so the Z transform of this one is 1 over 1 minus A Z inverse, and Z absolute should be greater than A absolute, right? So that means using this by comparing we can find the, so if you compare this with this equation, so you can easily tell that basically A is 0.5, so that means we can say that the first term has the inverse Z transform, right? So the overall is HIN. Okay, so the first term is for A we have 0.5, so that means 0.5, right, to the power n and u of n. So minus, now for the second term you can understand that 0.9 is the scaling factor, so because Z transform is linear, so if you scale the time domain signal, the Z domain signal will also be scaled by the same factor. So that means we can write this as 0.9. Again, Z power minus 1 basically indicates the shift, that the signal is 1 unit shifted, and shift is basically delayed, right? So that's 1 unit delayed signal. If Z power plus 1 was, then we would say that 1 unit advanced version. So this is again the same, so we can say that again 0.5 to the power, it will be n minus 1, and this will be u of n minus 1. So I hope that's quite straightforward, and it gives you the idea for the inverse system. So that's okay. So if this is your transfer function, the inverse system will have transfer function reciprocal of this one, so that means numerator of this one will become the denominator of this one, and denominator of this one will become numerator. Again, this is the scaling factor B naught by A naught, so it will become A naught by B naught. And then the important thing is that the ROCs of the two, that is the original system and the inverse system, they must overlap. Okay, so based on this condition we can easily find the not only the inverse system but also the impulse response of the inverse system. So here's another example that h of z is given to you, and you're supposed to find the inverse system and also the impulse response of that the inverse system, right? And also you can tell whether the impulse response you found is stable or unstable, right-sided or left-sided, meaning that whether it's stable and causal or it's stable and non-causal. So if we summarize, we say that if h of z is causal system with zeros, right, ranging from 1 up to m, all right, ck, 0 ck, and k is running 1 from up to n, then its inverse system will also be causal if and only if we associate the ROC is greater than maximum of ck, okay, with h inverse of z. We also required that the inverse system be stable, then the ROC of h inverse system must include the unit circle. You understand that, because system function can be found for both stable and unstable systems. But again, the stability criteria is same as we defined for the in terms of impulse response, that its impulse response must be absolutely summable. If the impulse response is absolutely summable, then the system is stable. So in case of the transfer function h of z, in that case we say if its rock includes the unit circle, then that system will be stable. So if rock include the unit circle, therefore it must be true that maximum of ck should be less than 1. So if this condition is met, then we say the system is stable. All zeros of h of z must be inside the unit circle. An LTI system is stable and causal, and also has a stable and causal inverse if and only if the poles and zeros of h of z are inside the unit circle. So if the system is stable, its inverse is also stable, then such a system is called the minimum phase system, which we'll discuss later. So impulse response for a rational system functions, because we understand that a system with only first order poles is basically h of z, and we have summation r running from 0 up to m minus 1 br z power minus r, and plus the k running from 1, summation k running from 1 up to n ak over 1 minus dk z inverse. Now again, if we also assume that this system is causal, then the impulse response of the rational system function will be given as h of n, and because inverse z of this one will be equal to summation r running from 0 up to m minus 1. You understand z transform is linear, so based on linearity we can we have the superposition here. Okay, so br, and this basically z power minus r represents the delay, so we can represent it by impulse n minus r, and plus the inverse z of this one will be summation again, because summation holds the property, the z holds the property of in general linearity, but also superposition, because we say a system is linear only if it holds the property of superposition and scaling. So we can say that's basically scaling factor ak, so we can say that ak, and the inverse z of 1 minus dk z inverse, so you understand this will be equal to dk power n, and because we say the system is causal, so that means it is right-sided, so we can taking the inverse z of this one will result into u of n, right? So I hope that's quite straightforward, but anyway, if you have any confusion, we can discuss it in the live session. So based on the nature of the impulse response, we have two important classes of LTI systems, that is the infinite impulse response system. So in this case, at least one non-zero pole is not cancelled by a zero. At least one term of the form ak dk n dk power n u of n we have, and h of n is not of finite length. It is not zero outside the finite interval. Okay. The second class of LTI system is called the finite impulse response, or FIR. In this case, h of z has no poles except at z equals to 0, that is n equals to 0. For this case, a partial fraction expansion is not possible. So h of z is simply a polynomial, and z power minus 1 of the form h of z equals to summation k running from 0 up to m bk z power minus k. So we can assume without loss of generality that a naught equals to 1. So in this case, the time domain for this one, that's the impulse response for this system described here, can be written as h of n summation k running from 0 up to n, a bk impulse of n minus k, and this is equal to bn for 0 to m and 0 otherwise. So the difference equation is for this one is identical to the convolution sum, that is y of n equals to summation k running from 0 up to m bk x of n minus k. So let's have a numerical example on the FIR, or finite impulse response system. So consider an impulse response, that is the truncation of the impulse response of an IIR system, with the system function given as this one. So the time domain for this will be the impulse response, and h of n is truncated, right? So that's the truncation from 0 up to n. So let's take the z transform of this system. So the let be represented by h of z. So this is equal to, right, to understand, to take the z transform, so you just take the summation and running from, because in this case we have just a finite sequence. Okay, so n running from 0 up to m, and we have af n into z power minus n. So using the summation equation, we see that this is equal to 1 minus a to the power maximum limit plus 1, right, into z power minus m minus 1, and this is divided by 1 minus a to z power minus 1. So let's express this in terms of difference equation. So we know h of z basically equals to y of z, right, divided by x of z. Okay, so that means we have this equation. So we can express by y of z will be equal to z of z times h of z. So we can write that y of z equals to x of z, h of z times x of z, right? So that is, we just straight away write summation, right, and running from 0 up to capital M, and we have a n z power minus n into x of z, because y of z equals to response or system function times the input. Now if we take the inverse z of both sides, it will result into y of n, right, inverse of this will be y of n, and this is because again summation, superposition, and this is how to say, the linear. So we can say that summation k running from 0 up to m, okay, and this will become ak, right, and basically this one represents the shift or the delay. So we can write x of n minus k. Okay, we can also use this part and we can find the difference equation. So again, you understand this is h of z, so multiplying this with x of z will be equal to, right, x of z multiply, right, and this will be equal to y of z. So that means because this is numerator denominator, it is divided this side. If I bring it this side, it will be multiplied. So let me write here, I can write that y of z into 1 minus a z inverse, and this is equal to x of z, right? Or let me write this, 1 minus a power m plus 1 into z power minus m minus 1 multiplied by x of z. Okay, now if I take the inverse of inverse z transform of this one, so you understand this y of z multiplied by 1 is y of z, and this is a z inverse y of z. So if I take the inverse Fourier transform z transform, so I hope that will be straightforward to you, and it will result to y of n minus a into y of n minus 1, and this is equal to, again, x of z multiplied by 1 will be x of z, so inverse of it will be x of n minus a, because that's scaling, so a power m plus 1, and again this represents the shift, so that means it will be x of n, right? So minus m minus 1. So you can see that basically we obtain two different forms of the difference equation from, one is this one and one is this one. Okay, so we obtain two different difference equation that are from two equivalent forms of the h of z in this equation. So we end the lecture here, and we'll start from this slide in the next lecture. So that's all from my side. Hopefully you will go to the video lecture and watch the whole video lecture carefully and note the points where you have some confusion or you want to discuss. Also, you must go to the numerical problems I have given you, so you must solve them, and this will help you understanding better concepts. So that's all for today. Allah Hafiz. Assalamu alaikum.